So we've got to take this one fraction and split it into two fractions. So what we're going to do is factor the bottom first. So that'll factor into x and plus 3 and minus 2. So then the idea is maybe we could split this up into something over x plus 3 plus something else over x minus 2. Because if you had two fractions like this, then when you added them, you would need a common denominator, right? And to get a common denominator, you'd end up getting this times this, which would be this common denominator. Okay, the problem is we don't know what goes on top here. So we're just going to pretend that we know and call it capital A. And then here we're going to pretend we know what goes on top here. We're going to call that capital B.
Why don't you just do 16 over x plus 7 minus 6 minus x?
Because I want to split it up this way, not that way. Yeah. But you're right. Technically that would follow the directions. But I've got a reason, and I'll tell you after we're done with this problem. Okay. So what I want is I don't want squares in the denominator. Okay, so I can tell you why. Because when you take the antiderivative of something squared in the denominator, that's tough. But if you take the antiderivative of something that has an x to a first power in the denominator, that's easy because that's an ln. Okay, good. All right, so we're trying to figure out what number should go up there and what number should go up there. And so we're just going to pretend that we know what those numbers are, and we're going to add these two fractions. So we would need to get the common denominator. So we'd multiply by x minus 2 over x minus 2. So then this fraction would end up being a times x minus 2 over x minus 2, x plus 3. So I just took this fraction and multiplied by x minus 2 over x minus 2 so I could get the denominator. So what do I need to multiply this fraction by? X plus 3 over x plus 3, right? That's legal because it equals 1. So then over here I'm going to get b times x plus 3 over x minus 2, x plus 3. So now I've got a common denominator, so I can add the two fractions together. And in the same step, I'll distribute the a and distribute the b, if that's okay. So this will be ax minus 2a plus bx plus 3b all over my common denominator. Okay, so then these two terms, those have x's in them, right? What do those need to add up to? Negative 1x, right? Everybody see that? What, the ax plus the bx need to combine to be negative 1x. So that means the a plus b needs to be negative 1. And then these terms are numbers. A is a number, so negative 2a is a number. And b is a number, so 3b is a number. So I'm taking a number plus a number, and what do those numbers need to add up to? 16, because that's the numerator. The number in the numerator of my fraction. So negative 2a plus 3b needs to be 16. So now I've got a system of equations that I can solve. So to solve that, I'm going to multiply the top equation by 2. So 2a plus 2b equals negative 2. I'm just going to leave the bottom equation alone. So why did I multiply the top equation by 2? So that the 2a and the negative 2a would cross out, right? So this is 5b equals 14. So then you divide both sides by 5 and you figure out that b is 2.8. How can I find a? Yeah, just put 2.8 here, right? So a plus 2.8 equals negative 1. So then you subtract 2.8 to the other side. So a is negative 3.8. So now what I've done is I've rewritten this fraction in a different way. It is negative 3.8 over x plus 3 plus 2.8 over x minus 2. Everybody did okay. Do you believe that this is the same as 16 minus x over x plus 3 times x minus 2? So it's just it's the fraction just split up into two fractions. Okay, that process that we just did is called partial fraction decomposition. And the decomposition, I think, Priyanka, means that instead of x squareds, now we've got x's. So it's becoming less complicated. It's decomposing in some sense. So if I'd said perform partial fraction decomposition, then there wouldn't have been any ambiguity to the directions. But I didn't want to use the fancy term before you knew what it was, so there you go. All right. Good. All right, so the reason we're doing this is because we want to be able to do integrals like this. Now this is a pretty tough integral because it's a fraction, letters on top and bottom. What's our tool that we have for doing tough integrals? It's called U substitution. So definitely maybe that tool will work on some of these problems. So don't write this down, but I'm going to do a U substitution. The U that would make sense would be the denominator. And then you would take the derivative of that, right? And then you'd move the 2x minus 1 over. So you'd have the antiderivative 16 minus x over u times du over 2x minus 1. Everybody with me? Okay, so why is that not working out? Because the 2x minus 1 is not canceling. So if that numerator was 2x minus 1, if we were doing the antiderivative of 2x minus 1 over x squared minus x minus 6, then U substitution would be the way to go. That numerator was 2x minus 1. But it's not, so it's not the way to go. But I'm just trying to don't forget about U substitution. It might work on some of these. It's our, yes, go ahead.
The other form of U substitution that we know using a derivative only works for multiplication, correct?
I mean, I don't want to say only and always, et cetera, but often it comes from a multiplication situation, yes. So that's the other tool you have.
So we wouldn't be able to use it?
Yes, and also it's an A-B day, so we know that we're not going to use it. But that's not true on the test, so that's a silly answer. But yeah, is it possible for me to cook up a division problem where UDV would work? I think so. But generally it's used for multiplication, yes. All right, so here's the idea. We know that this is equal to this, right? So instead of integrating this, why don't we integrate this? So in example 1, we did a lot of work to figure out that 16 minus x over x squared minus x minus 6 equaled these two fractions added together. So if you were just doing an integration problem, you'd have all that work to do to get from step 1 to step 2. But this time we already have it done. Okay, then how do you deal with integrals and plus? Yeah, you can take the integral of the first thing plus the integral of the second thing, right? So that's nice. And then this 3.8 here could come out in front of the integral. So it's negative 3.8 times the integral of 1 over x plus 3 dx. Because constants can come out in front of integrals, right? And then I'll do the same thing with the 2.8. Okay, then what is this antiderivative? Yeah, natural log comes into play. Why does natural log come into play? Because it's an x to the first power in the denominator, right? If it was x squared or x cubed or anything else, it wouldn't come into play. But since it's x to the first power, then the antiderivative is the natural log. So this antiderivative is the natural log of the absolute value of x plus 3. And the negative 3.8 just carries down. And then the 2.8 carries down. And the antiderivative of that is the natural log of the absolute value of x minus 2. Now, we know natural log comes into play because it's x to the first power. Why don't we have to worry about chain rule? Because the derivative of the x minus 2 is just 1, right? I mean, it's 1 minus 0. But chain rule is not going to come into play because that inside derivative is just 1. Okay, now if this is if this is a free response question, it's fine to leave it like this. But sometimes on the multiple choice questions, they get a little fancy with their logarithm rules. So I'm going to go a couple steps further just so you can practice those logarithm rules. Okay, so first of all, if you have a negative plus a positive, you could rewrite that as this minus this. So that's 2.8 natural log of x minus 2 minus 3.8 natural log of x plus 3. So I just swapped the 2.8 term and the 3.8 term and rewrote it as a minus instead of plus a negative. Okay, then what can you do with a 2.8, or what can you do with any number in front of a logarithm? It can be an exponent inside. So this is the natural log of x minus 2 to the 2.8 power. And then the next one is the natural log of x plus 3 to the 3.8 power. So from that step to that step, I just took the numbers in front of the logs and made them exponents. Okay, then what do you do with two logs that are subtracted? It's one log divided. So this can be written as the natural log of x minus 2 to the 2.8 power over x plus 3 to the 3.8 power. Okay, so again, if it's a free response question, totally fine to stop here. But I just didn't want you to, if this wasn't a choice, I wanted to be able to find this choice if it was a multiple choice. All right, so now we're on to example 3. And this time we're going to integrate 8x minus 7 over 2x squared minus x minus 3 dx. And we could try u substitution, right? That's our only other tool for hard derivative, antiderivatives. So we could do u substitution, but the derivative at the bottom is 4x minus 1. And that doesn't match up with 8x minus 7. Well, if it was 8x minus 2, then that would be twice the 4x minus 1, right? So then it would work out. But it's 8x minus 7, so it doesn't work out. Plus, we need to practice partial fractions. So probably it's a partial fraction problem. It is. But I just don't want you to forget about the other tools, because these antiderivatives are just going to be on there. It's not going to tell you what to do. You just have to try your tools. Okay, so first step for partial fraction decomposition is to factor the bottom. So this one factors into 2x and x, and negative 3 and positive 1. So we're hoping that we can split this up into a fraction that's over 2x minus 3 plus another fraction that's over x plus 1. And the reason we're doing that is then this antiderivative by itself is a lot easier than this one. Okay, so now we need to go off to the side and figure out what this capital A is and what this capital B is. And the way you do that is you pretend you know what they are and you add these fractions. So this fraction would need to be multiplied by x plus 1 over x plus 1. So that would be a times x plus 1 over the denominator. And then the second fraction would need to be multiplied by 2x minus 3 over 2x minus 3. So that would be plus b times 2x minus 3. So if we added them, the numerator would end up being ax plus a plus 2bx minus 3b. And we need that to turn out to be 8x minus 7, right? So that means we need the a plus the 2b to be 8, because the x terms need to come out to 8x. And then we need the a minus 3b to come out to negative 7. So there I have a system of equations that I can solve. Figure out what a and b are. I can just subtract the equations, right? And then the a's are going to go away. So a minus a is 0. 2 minus negative 3 is 5. And 8 minus negative 7 is 15. So last time I added the equations, because I had a negative and a positive, and they were going to cross out if I added. This time I'm subtracting because I've got two positives that will subtract to go away. So b is 3. And then to figure out a, just plug back in, right? A plus 2 times 3 equals 8. So I'm plugging into here, now that I know that b is 3. Times 3 is 6. 8 minus 6 is 2. So now I know, coming back over to here, that if I put a 2 up here, and a 3 up here, then this whole mess is the same as this. So I just split it up into two fractions. And the reason I did that is because now these are easier antiderivatives. Okay, so I'm going to take the antiderivative of the second one first, because that's even easier. I mean, this is pretty easy, but this is even easier. So picture the 3 coming out front. So it's 1 over x plus 3, right? So the antiderivative of that is 3 times the natural log of x plus 1. And there's going to be a plus c at the end. So then for this one, the 2 comes out front. And it's natural log of 2x minus 3. Except we do have to worry about chain rule on this, right? Because the derivative of that would be 1 over 2x minus 3 times 2. So we have to divide by 2 to compensate for that extra 2 that comes out. Or multiply by half, whatever you want. And then that's kind of convenient because that 2 will cancel out with that 2. So we have ln of the absolute value of 2x minus 3 plus, I guess I'll make this an exponent, ln of absolute value of x plus 1 cubed. And again, if it's free response, leave it like this. But if it's multiple choice, what's 2 logs added? 1 log multiplied. 2 logs subtracted is 1 log divided. But 2 logs added is 1 log multiplied, so it's natural log of the absolute value of 2x minus 3 times x plus 1 cubed plus c. Okay. So we've seen this differential equation a lot. dy dx equals ky. And the fancy way to say that is the slope is proportional to the y value. So this is the mathematical symbol way to say it, but if you wrote it out in a sentence, you could say the slope is proportional to the y value. Okay, so, and we've separated the variables on this a lot, right? Bring the dx over, divide by y, so it's 1 over y dy equals k dx. And then you do the antiderivative, and you get a plus c, and you're becoming pros at solving this one. Okay, so I can now tell you, that since you're really good at it, that every time it's going to come out like this. It's always going to come out e to the c times e to the kt. And this kind of a graph is called an exponential graph. And when you graph an exponential, it looks like this. Okay, so now, today, we're going to look at a new type of differential equation. It starts out kind of looking like this. So it's dy dx equals ky times m minus y. So it starts out exactly the same, dy dx equals ky, but then it's multiplied by m minus y. And by the end of the next couple days, we're going to have this filled in. We're going to know what the y equation is that goes with this. And we're going to know the name of it. And we're going to know what the graph looks like for this type of differential equation. Okay, but before we get there, we're going to look at one specific example. So about dy dx equals y times 4 minus y. You know what? I want to put a 1/2 here. 1/2 y times 4 minus y. Okay, so this template fits this. What's the k? 1/2. What's the m? 4. So in this type of an equation, the k is always going to be a number, the m is always going to be a number. It's just from different problems, the k and the m. Just like here, this k was always a number. It just changed from problem to problem. Okay, so what we're going to do with this is we're going to draw a slope field. I'm going to draw a slope field for this differential equation. So the first thing that I notice about this slope field, or about this differential equation, is there's not an x in the equation. So when I have a point, all I have to do is plug in the y value. Okay, so let's start with the point 2, 0. For the point 2, 0, what's the y? 0. 2 comma 0. That's all good. That's why I was asking, to get us thinking. So 2 comma 0, the y is 0. So we just take 1/2 times 0 times 4 minus 0. 4 minus 0 is 4. 1/2 times 0 times 4 is 0. So the slope at that point is 0. So we just draw a tick mark that reflects that, slope of 0. Okay, now moving over to this point, the point 1, 0. The y is still 0, right? So the slope's still going to be 0. So all of these slopes are going to be zeros all across the y-axis, because that's where the y is 0. So now I'm going to move to the point 2, 1. At the point 2, 1, the y is 1. So we've got 1/2 times 1 times 3. So 3/2. So we just need to draw a little line that we think goes up 3 over 2. Just eyeball it. And then 1, 1 is going to be the same, right? Because it has the same y value. All these points are going to be the same, because they all have the same y value. Okay, now moving to the point 1, 2. Now the y value is 2. So I have 1/2 times 2 times 2, because 4 minus 2 is 2. So that's 2. So a little bit steeper than this. Okay, now I'm going to move to 1, 3. Now the y value is 3. That's 1 then. So I have 1/2 times 3 times 1, so that's back to 3/2. So now it's less steep again. I'm probably drawing it less steep than, should be the same steepness as here because it's both 3/2. But I just want to know it goes from less steep to more steep to less steep. That's what I'm trying to get at. Okay, now to the point 1, 4. One half times 4 times 0. So a slope of 0 again, up there. Okay, so now that's the slope field, right? What do you get, though, if you trace out the slope field? What, yes, not what shape, but yeah, Dan's right. Yeah, I get an S shape, right? Good, that's good. But what are you finding when you trace out the slope field? What y equals, right? It's a way of solving this for y without actually having to do the whole separation of variables thing. So we've got a picture of the y if we trace this out. So Dan's exactly right. It looks like this. So it's kind of bad I put my slope field up here because I wanted to fill in this row of things, right? But that's just... Anyway, so this, when you have this differential equation, you get this kind of a shape for y, right? But if you have this differential equation, you get this kind of a shape for y. And notice it starts out exponential. Look at that. The first half of it is pretty exponential. But then it slows down. That's what the m minus y does for it. It's steep like an exponential to start with, but then this 4 minus y turns it back around and down. Okay, so I guess I'll put it over here. For dy dx equals ky times m minus y. Well, we don't know what y equals yet. We didn't separate the variables yet. We'll do that tomorrow. But we know that the curve looks like this. And this kind of a curve is called the logistic curve. And solving for y on this is going to take a while tomorrow. It's a tricky separation of variables problem. So we'll leave this blank for now, but tomorrow we're going to figure out what y equals. It's a pretty tough problem. You could say it's a logistical nightmare. Ha ha. We're not done yet though. I still got one more example. Oh, and I have another joke before I get to my last example. A rancher, did I talk about this yesterday? A rancher went out to his ranch to count his cows, and he counted 196 of them. And he came back and his wife says, "How many cows do we own?" And he said, 200. And she said, "Well, I heard that you only had 196. He said, "Yeah, but then after I rounded them up, there were 200. All right, one more problem. Let's say we're trying to take the antiderivative. So what am I at? Example 5 here? All right. Antiderivative of 7 over x squared plus 1 dx. So what do you think about u substitution? The derivative of x squared plus 1 is 2x, right? So if that was a 2x on top, or even a 7x on top, then the x's would go away, right? So u substitution is not the way to go. Okay, so our other tool is partial fraction decomposition, right? What's the first step when you do partial fraction decomposition? You got to factor the bottom, right? Does x squared plus 1 factor? It does not. X squared minus 1 factors into x plus 1, x minus 1. But x squared plus 1 does not factor. So that means u substitution doesn't work on this. Partial fraction decomposition doesn't work on this. But it's not a hard one. Here's what you got to do. Bring the 7 out front. And then what's this antiderivative? Nope, that would be a chain rule. Natural log does not apply because x is to the second power in the denominator. If you did natural log of x squared plus 1, that would be 1 over x squared plus 1, but then times 2x. So that's back to that u substitution that we needed. We needed there to be an x up there. The integer of this is inverse tangent. So it's easy if you have it memorized, but it's not if you don't. The derivative of inverse tangent is that. Therefore, the antiderivative of that is inverse tangent. 7 comes down, plus c. So that one's annoying if you don't remember that antiderivative, but it's really easy if you do. All right, thank you for listening.